So here in section 11.3, we're going to talk about our model assumptions. So we assumed that our linear regression model was of the form beta 0 plus beta 1x plus epsilon, where epsilon was a random error. And now we want to study that epsilon. So that epsilon, that random error, is actually going to have a probability distribution. And we've got some assumptions that we're going to make about that probability distribution for epsilon. First of all, the mean of that probability distribution is equal to 0. So in other words, the expected value of epsilon, the expected error, is 0. So that means if you take the expected value of y, which is the expected value of this quantity, the expected value of the epsilon is 0, so the expected value of y is just beta 0 plus beta 1x. Also, the variance here of the probability distribution of epsilon is going to be constant for all x values. We'll call that variance sigma squared. And then the probability of distribution of epsilon is normal, so it's a bell-shaped curve. And then the values of epsilon here from different values of y we're going to assume are independent. So here's a picture of what's going on. We've got our y-axis and our x-axis, independent, dependent variable. Here is our model line, beta 0 plus beta 1x. And then for each x value, we've got a probability distribution of the errors. And here we've shown 3 different x values, 5, 10, and 15. So positive errors are above the model line. Negative errors are below the model line. Notice that the mean of that distribution is 0. Epsilon equals 0, which means that the mean of the distribution sits on the model line. And we're also noticing here that this is a bell-shaped distribution, normal distribution. And then the variance is constant for all x values, so that's saying that the width of these distributions here is all the same. So all of those probability distributions are identical, and they all sit along the line. So we might want to be able to find this sigma squared, the variance of that probability distribution. So let's look at how we could estimate sigma squared for our first order or our straight line model. So sigma squared can actually be estimated by s squared, which is the sum of squares of error divided by the degrees of freedom for error. So that's SSE over n minus 2. Remember SSE, that is the quantity that we minimized to get the least squares model, right? Sum of squares of error is the difference between the y-coordinate on the point and the y-coordinate on the regression line, and we square that. Well, we can also, it's also the case that sum of squares of yy minus beta 1 times sum of squares of xy is sum of squares of error. So that is algebraically equivalent. And that's where sum of squares of yy is the sum of the deviations of the y-coordinate from y bar squared, which is the sum of the y squares minus the sum of the y's squared over the sample size. So then if you take square roots of both sides of this, your sigma is approximately equal to s, which is the square root of SSE over n minus 2. And that's called the estimated standard error of our regression model. So let's consider our example that we looked at in the previous section. So we're modeling linear relationship between a dose of medication in milligrams and perceived pain level in y. So here's the extensions table all completed. We completed everything before except the y squared column. So these are our sums of the various variables on the bottom. We also had computed beta 1 hat was negative 0.00861, beta 0 hat 8.478, and then this was our model to 3 decimal places. We previously computed sum of squares of xy to be negative 2475. We now need to compute sum of squares of yy. So the sum of the y squared column, that's 133. Minus the sum of the y column, 21. And that gets squared. And we're divided by n, which is 4 ordered pairs. So let's go ahead and compute that. So the sum of the y squares is our 133 minus alpha y equal enter. We had 21 squared in the numerator, divide by 4. So 91 fourths, which is 22.75. Whoops, 22.75. And so then our SSE is going to be sum of squares of YY, 22.75, brought that down, minus our beta 1 hat, which is our slope, negative 0.00861. And then times sum of squares of XY, which is negative 2475. So let's go ahead and compute that quantity on the calculator. So that is going to be 22.75. Double negative there would make a positive times another negative is negative. So minus 0.00861 times 2475, 1.44025. And so then our S here is going to be square root of SSE over n minus 2, so 1.44025. And then we are dividing by n is 4, 4 minus 2 is 2. So we want square root 1.44025 divided by 2, 0.8486. And then the interpretation of this value S is that we would expect approximately 95% of our observed Y values to lie within 2 standard deviations, 2S, which equals 2 times that 0.8486, that distance of the predicted Y hat values. And let's take a look at what Jamovi output would look like here. So this is the same output that we had before. It's our linear regression with R and R squared. Again, we have not done that yet. Our ANOVA table. And our model coefficients. So that's what we had before, and the important things that I want you to observe is under the residuals here, sum of squares, 1.44, and our sum of squares of error, 1.44. So that is our SSE. So that value right there is SSE. And then under the mean square column, this right here, that is S squared, that 0.722. So that tells us then that our S is going to be square root 0.722. Compute that on the calculator. So second square root 0.722. We get 8497, so this is approximately 0.8497, and we had 8486, so 9786. We've got a little bit of round off error there. Okay, so that is our S here. So this one is more accurate. Here we've got some round off error because we did not use all the values in the slope, so that would change things slightly. So that's what we're seeing.